If you followed my channel for a while, you know that I'm really into networking, home lab, software kind of stuff. But my actual formal training is in computer engineering. So that's sort of low-level programming, assembly, C, boot banging hardware, that kind of stuff. So, since I have a big milestone coming up soon of 100,000 subscribers, I thought I would take a trip into the real world and make something physical for once. So, armed with a box of finished beef jerky for motivation, and a small desktop CNC machine, I'm going to make something for my desk that reminds me about all of you guys, how many subscribers I have. So I've given myself, I don't know, about a month or so to get this project done, and let's see how I do. So if you're interested in seeing me, a computer engineer who now does networking, trying mechanical and electrical engineering, then come along on this adventure. But before I can go off just building something, I need a plan. So what do I want this thing to look like? Well, I want to put it on my desk, and currently I have about 94,000 subscribers, so I need 6 digits to hold 100,000. So 1, 2, 3, 4, 5, 6 digits in some sort of rectangle, whatever. I don't need a 1,000 separator, just the 6 digits. Even though I can't imagine actually designing vintage electronics, I'm also quite inspired by some of the channels that do work with vintage electronics, such as, say, like Usagi Electric with his Centurion mini computers from the 70s, that sort of electronics era. And I also really like Nixie tubes, which look like this. They were never that common out past like the late 50s, early 60s, because we had better technology in the US, but they were very popular in the Soviet Union for a long time, so you can still buy new old stock from there. That also means that my comfort zone of designing 1.5 volt and 3.3 volt electronics, which is mainly where I've operated in for the past most of my career, means I have to touch 5 volt electronics, horrors, and even high voltage stuff, which I've done in a sort of tangential way before, but not really had to design circuits for myself. So, back to the plan. So the plan, first, I'm going to design the enclosure in CAD. I use Onshape for this, so we'll do Onshape. Then, I am going to design the electronics. I'm going to use KiCad for this. KiCad is open source. Then, I'm going to make all of the parts. So I'm going to mill the enclosure out of a block of wood. I'm going to mill the circuit boards for my schematic out of, well, circuit board. Then I'm going to assemble and test it all. And hopefully, by the end of this video, I have a working thing that resembles a clock, but actually tells me how many subscribers I have. So that's the plan. Let's get started with the CAD. So first step I had was to make a model of a Nixie tube. So I found an old Soviet data sheet. I tried to make all the pins in the right place, length, size, things like that. Tried to round it over, get the dimensions accurate, etc. And I think I got a pretty decent model of a Nixie tube. So now the next step is I need, well, 6 of them. So probably should have used a pattern, but I initially just didn't. So here I am going back and using a pattern. So I constrained them all to each other to be on the same plane. I got them all spaced how I want. So I think the digits will look good at the spacing. And now based on these 6 tubes here, I'm going to start drawing the enclosure. So I want a specific gap. My thought was sort of to have a nice piece of brass to reflect. Maybe I'll have some inspiration pic to show you, I don't know. And I just sort of extruded that shell out. So that's sort of what I want the outer enclosure to look like. I just sort of made it arbitrary depth, but I guess I'll figure that out later. So next step, I beveled all the edges inward, and I played a little bit with how deep I want the tubes to be. So then I added a separate part on the surface that I'm going to use as a piece of brass, which is hopefully going to reflect the glow of the tubes and look really cool. So that's sort of a rendering of what it'll look like. Rounding the corners off a bit because it'll probably be made out of a single piece, or I don't know how I'll make it yet. They're all floating away on me. So with that created, I need a circuit board to represent, well, circuit board. So here I am modeling the circuit board just for the tube holes and things like that. So that helps keep the tubes constrained in space. So now I can play with how deep the tubes are with constraints and see if I think the dimensions are good, if I want to make it a little bit bigger, etc. And here you can kind of see a cutaway of what it'll look like on the inside. So let's get to making it. Oh my gosh. Oh, this thing is heavy. So this whole video was made on the Carvera Air desktop CNC machine. So Makara kindly sent this machine over for me to make this video. So more about that later. Okay, so I've been like super unmotivated recently. So I picked the machine up and I put it here on the table. It is freaking heavy. So that will force me to get this project done because it can't leave the table until it's done. I also am actually coming quite close to my 100,000 subscriber milestone. So I'd like to have this project entirely finished before I actually get there so that I can actually enjoy seeing it roll over to 100,000 with it working and everything. So I'm currently about 4,000 to 5,000 subscribers away as of when I'm filming this segment. So I guess we'll see how close I am when the video actually releases, but good motivation for me. So I think I have all the parts now. So I got the machine, I got wood, I bought some 4x4 posts that I'm going to mill out. I got a piece of brass from the knife guy, and I bought all my electronic parts at like midnight at one point without drawing a schematic. So now I actually have to go back and draw a proper schematic so I can make a board design. Oh yeah, I don't think I mentioned. So because I'm making this out of tubes, which are kind of a vintage technology, I kind of want to keep that whole aesthetic through the whole project as much as possible. So I'm using single-sided PCB boards, which come just flat copper. I'm going to mill them on the Carvera to the circuit designs. Now because they're single-sided, obviously I'm going to have a hard time with a bunch of the routing and stuff like that, which is something I totally anticipate. But I'm going to make it 3 PCBs thick. So I'm going to have one PCB that's just breaking out all the pin headers from the tubes, and another layer that has the high voltage drivers, and a third layer that has the low voltage, low voltage power supplies, and also the ESP32 is going to control all this. So I'm going to start with the tube board because it's the easiest, and see if I can get that designed. I guess first though I should show off some of the parts I got for this build. So this guy came to me from Ukraine, and it includes these guys here. So unroll one of them for you. So here is the beautiful Nixie tube, centered. This is the IN14. So this is going to be the digit tube. I ordered 12 of them, but I only need 6. So I flip it over on the back. We got 12 pins here. One of them is the high voltage, 10 of them are digits, one of them is not connected. So I'll need 12 sockets in my board to hold 6 of these tubes and to drive them with 185 volts. So everything else came to me from DigiKey. And what better way to open this than a traditional Finnish puukko set? Both of them. Big guy here from Isaki Jarvenpää. Let's go. Oh. Smaller one is for disciplining your kids, by the way. Got in troubles with my neighbors recently because apparently this doesn't count as paper for recycling. I don't know, we don't recycle in the US, so I'm not used to this whole having 5 bins of recycling stuff. So I designed this whole thing in my head while ordering parts, so I could have missed some. What did I buy myself? 470 k ohm resistors. Bought a shitload of those. Transistor, NPN, 300 volts. Resistor, 15.4K, 0.6 watt. Bunch of little connectors. Hopefully this is enough. I think I ordered enough. Big capacitors. MOSFET in-channel 500 volt. Inductor. Regulator linear 3.3 volt. That'll power the ESP. So, when I bought all these resistors, I had purposes for all of them in my head. So hopefully I can put that back on paper. So I got the schematic done without filming it. Now I'm working on layout. So this particular circuit is the high voltage switches. So I have 3 banks of 2 tubes each. They each need a high voltage switch. So I'm laying out the PNP and the NPN transistor and some of their base resistors. As I went through this, I changed the footprints of the parts back and forth to make the resistors sort of fit better if I want to stand them up or lay them down, or etc. As I was going to, I was also changing the connectors of my own pinouts as I went, just to make it easier to route. So here I'm moving around some of the pins in that connector so I can just do a straight shot in without having to jump over anything. And I also left a nice big space in the center for the high voltage boost converter so that all the paths there would be nice and short and there wouldn't be a lot of large current loops in the system. So I did think it through mostly, pretty much. And since I didn't film the schematic while I worked, here's kind of what the schematic looks like. So zooming in a bit. So on the tube board I have 6 tubes. Those are V1, 2, 3, 4, 5, 6. These are the 6-digit tubes. Each one has 12 pins, so I have 10 cathodes for the 10 digits, 1 anode, and the 12th pin is actually a decimal place, but I just have that not connected. So then I've got 2 sets of the same schematic here. That's basically going to a 10-pin connector for the 10 cathodes, and another 10-pin connector for the 3 anodes. And basically I use the 10-pin connector just for more mechanical stability, having more pins. And then this circuit's duplicated up here, so I'll just have to mill out this whole thing. The next board in the stack up is the high voltage board. So this needs to drive, well, all the high voltage. So on the power board, I've got the cathode drive, so I got the 10 pins coming in from the cathode board. I rearranged all these wires to make them easier to route. And then they have some 470K resistors just to prevent some leakage and ghosting on the tubes. The tubes are actually driven by this, which is a Soviet IC, a K155, that thing. So this is a dedicated Nixie driver IC. There was an American version of this, an SN74 series way back in the day, but this is much easier to get actually. So these guys essentially take in binary coded decimal on the input over here, and they drive the 10 cathodes over here with the high voltage cathode drive directly. So it's essentially like a 4 to 10 decoder where the extra 6 states are just not brought out. And of course I have a second one, so this is the other half of the cathodes. So at any given time I'll have 2 tubes lit, one from the top half and one from the bottom half here. And then here I have the 3 anode connections going to the 3 anode selectors. That's what I mean by having 3 banks of 2 tubes each. So I have 2 low side drives and 3 high side drives. High side drive is made up of a PNP transistor driving an NPN transistor. So we've got the PNP coming in through the 15.4K current limiting resistor to the tube from high voltage, and then a circuit to drive it from 3.3 volts from the micro. Moving over a bit, I've got the boost converter. So 12 volts comes into the board. I've got 2 bulk capacitors here, so I can put them close to the sources of noise. And then I've got the 100 microhenry inductor going into a MOSFET that's going to drive the high voltage boost. So then when this turns off, it'll drive a high voltage spike out of the inductor through this diode and into these 2 capacitors. These are high voltage ceramic capacitors. That gets us our 185 volts or so. And I got a voltage divider here. I wanted to protect the ESP, so I'm just using a diode for that. But that means that my analog scale is very low. But that's okay because the ESP analog input's only like 0.9 volts anyway. So 470 to 1 voltage divider. I've also got a 5 volt supply, just a linear LM7805. And again, some more capacitance that I can move around as I lay out for better noise. And the input is from a barrel jack. So the third board is the ESP board. So here's the connectors up to that board. And then I'm going to use an ESP32 C3 room. And I'm using literally every single pin on it. So I got 2 pins dedicated to UART that I didn't have to reuse for I/O. And then every single other pin is going to something. So these are mapped based on what's easy to route. But essentially I've got, so the C1 and the C2 are the cathode drives A, B, C, and D, and then I've got high voltage drive for the boost converter, high voltage feedback, and the 3 high sides. And it's driven by 3.3 volts, of course, so I need a L78L33 linear regulator. And I was able to put a programming header on, but I had to do some jumpers, so I put these in to make a manual jumper for layout reasons. And with the layout done, I exported those files into Macaracam. This is a software that's free for Carvera owners, so it can directly import the PCB files. So if I hit import here, it can directly take my Gerber files from KiCad, and then it imports them all as a bunch of different layers. So this is what my tool paths look like for the power board. So this is what that copper layer imported as, so the traces. Then if I turn that off, here's the actual cut path. So this is the path the machine is actually going to take, and it's pretty easy to define. So they just have some options. I'm doing a 0.07 millimeter depth of cut with my V-bit. I chose to use the 0.2 millimeter engraving bit. They have a library of all of the tools that they sell. So I'm using an engraving bit, single flute metal, this, and they have all the machine parameters for all the different materials. So I'm using PCB, for example. They have spindle speed, step over, step down, feed rate, all predefined here. So I can just choose that, and all these parameters will just fill in automatically, which is super nice. In this case, I'm doing a contour path, so it's following the curve from the Gerber file, but it's offset by the width of the tool, essentially. I also did all the drills here too, so these are all the different drill holes. They each import as a separate layer, so it's kind of handy to pick the specific diameter. So I used a 0.6 and a 0.8 millimeter bit just to make it a little bit faster. So for this one here, T3, I guess this was the, what was this one, 0.8 millimeter bit. So I just did a contour path where it just outlines the hole with a 1.5 millimeter depth of cut, so pretty simple. I think I was doing a step down here, yeah, so 0.3 millimeter step down. So it'll take steps, so it'll go down, circle, etc. And this worked pretty well. Last operation then is to cut out the board. So I just picked the outline cut that came in from KiCad and had it run with a really big end mill cutout. So I used a, was it 3 millimeter bit, and just outlined that. So this then exports the G-code, so I can choose if I want to skip any operations. Like I skip the cutout on a lot of these, if I want to probe and make sure that it actually worked before I do the cutout. And then this generates the G-code for the machine. So if you've never seen G-code, this is kind of what it looks like. There's a bunch of commands. So T, this is telling me to switch the tool to. M are machine codes, and then G are movement codes. So in this case, it's telling the machine to move to this X and Y coordinate, and then S12,000 is spindle speed. And then all of these G1s are just telling it to do some sort of move action at the feed rate. In this case, that would be, I guess, 500 millimeters a minute. And so this is the actual code that the machine executes, and it's super long, but I didn't have to write it, so that's nice. And so once the cam is done, I can actually make stuff. So with it now being time to make stuff, I started looking at all the parts to the Carvera Air that I had, all the little boxes and stuff that were all packed inside, and just kind of figuring out what I had, so then I could learn how to use the machine. So I got the machine to power on and home itself, and eventually hooked it up to their app, which is open source, by the way, probably Electron based. Then of course I had to break down and read the instructions. Just kidding, the instructions were actually really good. They had a series of example projects. I didn't make any of the examples, but I at least read them all, because they have a lot of good information on how to set up the machine and work holding and tool selection and stuff like that. Now the machine also came with this toolkit, so there's a number of hold down clamps, screws, 3 millimeter driver, stuff like that, just to do work holding and basic stuff. So I decided to try test cutting the PCBs first with just a single tube. And my very first cut here, the machine just cut a bunch of air because I had some settings wrong, but we're getting there, we're figuring it out how to use this thing. So then I got the machine to actually cut the board. So here it's using a 0.2 millimeter 30-degree engraving bit to cut out the space between the traces. So it outlines around the trace, and pretty much worked. I mean, I had to learn some of the settings to dial in, but I was pretty happy for a first cut. Also had my first bit casualty. This one was entirely my fault, but oops. So, wanting a bit more help with the machine, at this point I moved it over to the Sanioki Hack Lab. That's a makerspace in downtown Sanioki that I'm a member of. So here I am with the machine in the Hack Lab, and I'm cutting out the tube board. So I've got 6 tubes. They're both basically 2 copies of the same part of the circuit. So the machine is outlining all of the traces with an engraving bit. So it's cutting the copper away from, well, I guess the rest of the copper, to leave a trace behind. So it looks like it's already finished the left half, and it's moving on to the right half now. This is at 10 times speed, by the way, so it's not that slow. And overall, making this board with the 6 tubes, including doing all the mesh probing, tool changes, and drilling the holes and cutting it out, it took about 30 to 40 minutes. So really not terrible. I actually ended up cutting out my prototype board about 4 times, and I cut out this tube board, I don't know, maybe also 4 times. So I was learning some of the optimum settings for the machine. I mean, I'm asking it to do a 0.05 millimeter depth of cut with an engraving bit and a tolerance of like 0.01 millimeters, which the machine is certainly capable of, but the material might not be that flat even. So then the depth of cut changes, etc. Mesh bed leveling helps to some extent, but I was going through here probing to see if anything was bridged or shorted. And I did a number of different test cuts at different depths, different trace widths, things like that, to figure out what I was capable of making on this machine. Now, what I didn't have any problems with was making the housing. So I made this out of a solid block of wood. This is a 4x4 post. I just let the machine mill it, hog a bunch of the material out of the center, and do the sides with a finishing pass after this. And this turned out great. It just took like 6 hours. So then I took my boards home to solder them up with my little battery-powered soldering iron here. Now this board only has 0.35 millimeter wide traces. The power board has some 1 millimeter wide traces, which sunk a bit too much heat for this soldering iron. So I'm just using these little press-in sockets. I think Usagi Electric uses something very similar for his vacuum tubes, but they just fit a 1 millimeter pin, and they actually save me a lot of depth as well because I don't have to put the socket out in front of the tube. So I'm actually soldering on the back side here as the copper's away from the tube, but this worked pretty well for me. I'm not the best at soldering with like the uncoated no solder mask PCB, so I got out my multimeter here just to probe and make sure I hadn't shorted anything, no solder bridges, stuff like that. Went over the whole board and eventually got it perfect. So next up I'm working on the power board here. So I soldered this whole thing at the lab. And then now this is me and Iris at the lab trying to bring it up, like one circuit at a time. And I'll be honest, it was rough. So we started with the signal generator on the scope, trying to use that to drive the high voltage, to bring up the high voltage. That was our biggest struggle, was getting that high voltage MOSFET to turn on, turn off to generate the boost supply flybacks. And it was pretty rough. The circuit had some design errors, which I'll talk about a bit later. But we were clipping on with the Hack Labs oscilloscope. I brought my portable oscilloscope multimeter, using the power supply from the Hack Lab, stuff like that. And so we were fixing solder bridges as we went, fixing traces that I messed up a little bit while soldering, and also trying to get the whole thing to work. And we spent about 5 or 6 hours on this, I think. Another thing that turned out very nicely, I thought, actually, was the housing. So I used a, what Americans would call a 4x4 post. This is 90 millimeters square. My initial thought was I didn't want to have a lot of machining time with an 1/8 inch 3.1 millimeter bit hogging out the whole center here. So I thought I'd do that on the drill press. And same with the outside, so I thought I'd do that on a bandsaw. So I just had the machine cut the A-surface on the front, the nice curvatures, stuff like that. And so this is what it turned out like. So I had the machine cut down to the surface. I did a nice finishing pass here, which turned out very nice. So they went in different orientations for each pass, but that's okay. Then I came to the drill press with a big Forstner bit, took a bunch of stuff out. That didn't work the best, as you might be able to tell, but that was me hacking at it with the drill press. So after making this took about 2 hours on the mill, by the way, mostly because the finishing pass had such a small step over, it had to go over and over and over and over again. So that was my fault for just setting that setting too small. Then I learned after this that the saw we have in the Hack Lab is not actually a band saw. It's like a reciprocating, it's for cutting wood, like an oscillating saw. Wasn't quite big enough for this 90 millimeter stock. It could only do, I don't know, 50, 60 millimeter thick stuff. So I had a huge block of wood left that I wasn't going to cut by hand. So I decided to do a small redesign of the tool path so that the machine could do it. So this I did in 3 setups. Guess I'll show you on the close-up camera. So I had the machine go as deep as I reasonably could. My limit here is the Z travel. So this piece of wood is 90 millimeters thick. You have a drill bit here that needs to get down in that deep. So the machine needs to be able to retract up to this height with the height of the bit still. So the spindle's up here. And so with the tools I had and the clearances I had, I could get down to about here with one tool. I could have probably figured something else out after I cut the back, but I didn't. So I got down about 25 millimeters or so from the top surface. This one I ran a much quicker finishing pass, as you can probably see. So it still has a little bit of texture left, but it's pretty easy to sand off. And the brass will cover it up anyway. So this was with an 1/8 inch end mill to cut this, and then a 2 millimeter ball nose to cut the finishing pass. Now you might notice that this is a bit smaller in this dimension as well. and also this dimension. So I did all of that material removal on the Carvera as well. So I set it up this way, and at that point there was probably 10-12 millimeters of material here and still a little bit on the ends as well. And so I had it surfaced just at 2 millimeters at a time all the way down. And that took forever, but it ended up with a really nice surface finish. Then outline, so that got rid of, cleaned up the ends. I was better about cutting on the saw, so this is the original end. So it just trimmed off this and any excess on this side as well, and it did a good job. So then I flipped it over, and this one has a bit of a bevel to it that I don't know if you can see. And that's actually the bottom, so the thought is with that on the bottom, it'll sit upright a little bit on the desk. And so I did the same thing on this one. It went back and forth to take 10 mils of material off. Then it did the bevel, step by step by step. This one I did not use a ball nose, I just used a flat bottom end mill. So I'll just sand this a little bit because there's just a little bit of texture to it that you might be able to see from the steps of the step down. And that's fine again. So I just have to clean up this little bit here by hand, and the machine did a really nice job. I still have to hog out some material from the center, but I have this hole here that I used for fixturing, so I drilled a hole all the way through and bolted it down to the table. And that's what I'm going to use to run the power wire out, so I put it in a strategic place. But overall, I was really happy with how easy it was to do this woodworking on the machine. So I guess it's time for like the big reveal you've all been waiting for. And unfortunately, I got one tube to light 3 digits. And that was entirely my own fault for designing bad schematics. So I, being a computer engineer, copied several schematics from the internet, many of which were designed for Arduino boards. So Arduino operates at 5 volts. I'm using an ESP32, which operates at 3.3. I was aware of that, and I adjusted the base resistors and things like that. One thing I forgot to consider was the MOSFET for the high voltage driver. And that is absolutely critical because without high voltage, I can't drive any tubes. Also, while soldering the board, I broke off 2 traces, which is why I only have 1 tube instead of 6. So sorry about that. As for the high voltage driver though, I got a real Arduino that I borrowed from a friend, and unfortunately for me, 5 volts was still not enough to drive the MOSFET because the schematic I copied it from was driving it from a 555 timer, which I didn't notice was powered by 12 volts instead of 5 volts. So that means I need 12 volts into the gate of the MOSFET. I need to switch it really fast because the turn off time is very critical for a boost converter to get a good flyback pulse, as you maybe will be able to see on the scope when I start testing it here. So then I added a PNP transistor to pull up the gate to 12 volts. That then needed a level shifter, so I have an NPN transistor to drive the PNP transistor from the Arduino. And a wild collection of resistors here, different base resistors, pull-down resistors to bring the gate back down to 0. Unfortunately, what I probably should have done was used a PNP-NPN pair, so PNP on the top, NPN on the bottom, to drive the gate, and then driven that with the NPN. But I got this to work, so we're sticking with it. And I guess now it's time to finally plug it in. So this clip-on here is connected to 12 volts from the bench supply. I am so tightly integrated in the bench supply that this is not going to fit in the beautiful enclosure I made. And it doesn't seem to work unless the scope probes are plugged in and I'm looking at it, because as soon as I take them all off, it stops working. So here we go. There we go. We can hear it hum. I don't know if you can hear that sound. It sounds awful in person. So that's like 15 kilohertz or something, high-pitched squeal. That's the boost converter boosting up to 180 some volts. Looks like right now we're at about 130, which makes sense because I'm on the tube drive circuit with the scope and not the boost converter circuit. But yeah, we got 1 digit to display 3 digits. And I think the reason it's not displaying all 10 is because I have a trace shorted on the Soviet ICs. And just for a bit of a cool view on the scope here, the yellow trace is the high voltage select, which picks one specific tube. So this is running for, looks like 1.64 milliseconds out of maybe 7. So this is the time the tube should be fully on or off. These other 2 here are the high voltage. So if I zoom in on one of these guys, we can see this is the actual turn on, turn off of the high voltage drive. So green is the signal coming out of the Arduino. Blue is the signal that actually makes it into the MOSFET. This is the actual gate signal on the MOSFET. You can see it's coming up to 12 volts. And as soon as I power on the circuit, we should see the high voltage come up, and you can see a bit of noise coming in on the scope, the boost supply. So if I switch over now to look at the high voltage, this is the voltage actually going into the anode of the tube. So we can see the tube anode is 120 or so, so not too bad. We obviously have some glitching here. That's probably just caused by software timing not being super precise on these. So I'm a computer engineer. This sort of view on the scope is much more like what I'm used to working with than actually designing circuits. So when I've worked professionally before, I've done a lot of work in low-level software. So like the electrical engineers would talk to me and they'd be like, we want to pulse these switches in relation to these current signals, voltage signals, whatever. We would sit down at the scope. I would be debugging the code that makes these pulses flow. I was not designing the gate drive circuitry. They were doing that. So, oops, I guess I'll have to make a new board with a better gate drive circuit. So that's all I got for today. Thanks to Makara for sending over the Carvera Air. It is now living over there at the Sanioki Hack Lab. If you're in the Sanioki area, which I don't think many of my viewers are, but you're welcome to come over and play with it at any time. Thanks to these two guys here from the Sanioki Hack Lab for really helping me out in this video. I got a Discord server link down below for that, and I'll see you guys on the next adventure.
Bye. Bye.